Question one is talking about naphthalene. Now, naphthalene is mothballs, and if you don't even know what mothballs are, that when you store away things like sweaters and stuff, sometimes little moths will get in there and lay their eggs, and when they hatch, they will eat little holes in, especially like wool sweaters and stuff. So apparently, mothballs, kills off those larvae, so that doesn't happen. Anyway, so here's like little mothballs inside of a case. But we're saying that what mothballs does, it goes directly from solid to gas, it sublimes. So you could look at this and say, well, if I have a solid going to a gas, that is definitely going to require some energy, some heat energy. So it's going to be endothermic reaction. So if we take something, that happens at 25, put it at 40 degrees, that's going to force it forward. And if we have this in a little container, insulated container, and we have something that is absorbing heat, then the gas inside there is going to lose a little bit of its energy, so the temperature of the gas, which is our surroundings, is going to decrease slightly. So we have an endothermic reaction that's going to absorb energy from the gas. Number two is about a sample of water is placed in a cylinder with a piston against a constant external pressure. How is the internal energy of the system changing when the sample condenses? Okay, well, this is talking, you can hear this is going to talk about work, and work is P times delta V. And the idea is the work being done by the system or work done on the system? So if we had a container where the gas inside here was expanding, that would mean the system was doing work and losing energy. So it was going to condense. That means that work is being done on the system, and it's going to increase its energy. So the change in internal energy of the system cannot be determined? No. The internal energy is decreasing? No. The internal energy is increasing, or remains the same? No. Okay, so it's increasing because since it's condensing, then work is being done on the system by the outside atmosphere, the pressure. Number three, a cup of water at room temperature is placed in a tub of ice. Which of the following takes place? Okay, so we have a cup of water is placed in a tub of ice. So here we have our water, and now we have this big tub here, and this is full of ice. Okay, so what's going to happen? We know that this water temperature is going to go down, okay, and it's going to cool down. So the attractions between the molecules in the ice are weakened. Okay, well, this is a room temperature water, so yeah, so it's going to warm up the ice a little bit. It's going to weaken their attractions. So yes, so the attractions in the molecules are weakened, and if that's the same pattern, the attraction between molecules and ice are weakened. The attraction between molecules and ice are strengthened. That's not going to happen. Okay, so we can knock off C and D. And I'll finish the answers. Increasing the motion of water molecules in the cup. Well, the water, okay, which is a room temperature around the ice, which is 0, okay, they're going to be slowing down. So they're not going to increase the motion of the water molecules. They're going to decrease the motion of the water molecules. So our answer here must be B. Let's go to the next question. When 0.1 grams of benzoic acid and excess oxygen is ignited in a bomb calorimeter, the temperature of the water changes from 25 to 25.225. Okay, that makes sense. The heat capacity of the calorimeter is 603 joules per degree. What's the energy of this sample of benzoic acid? Okay, well, the fact that it's a 0.1 gram benzoic acid, that really makes no difference in this case. We just want to know the energy, not like the delta H. So we're looking for Q here. Now, because this is an object, okay, a bomb calorimeter, then instead of getting, the specific heat capacity, this is just going to be the heat capacity, joules per degree. And what that's saying is that we can say how much energy it takes for this object, for this calorimeter, to be changed by 1 degree, 603 joules for every degree. So how much we're changing? 25 and 25.225. So we have 0.225 degrees times 603 joules per degree. And that's all we have to do. So let's multiply those two. And from that I get an answer of 135.675. The closest answer here is 135. Okay, really ought to be 136, but that's okay. So that's all we need to do with that question. Okay, number 5. Using the enthalpies of formation given below, calculate the delta H of combustion for propane. Okay, so that means we have to imply that we're going to do an equation here, and we can do this. So C3H8, combustion, so we know that that's O2, turning into CO2 and H2O, and 3 CO2s, 8 hydrogens, we have 4 H2Os, count that up, that's 10 oxygens, so we have 5 O2. Okay, so using these enthalpies of formation, then we know that it's going to be the energies of the products, so 3 times this and 4 times this number, minus this one, and the energy of oxygen is going to be 0, because this is heat of formation, which is formation from its elements. This is already an element, so its value is 0. So I'm going to have 3 times CO2 negative 394, okay, that's kilojoules per mole, plus 4 times the water value, negative 286, okay, minus the C3H8 value, minus a negative 104. And if I do all that carefully, I get negative 2222 kilojoules per mole. And that's my answer. Okay, number 6. As ammonium nitrate is dissolved in water, the temperature of the system decreases. This process can be thought of in the following steps. Okay, so we can take that. Now, this is one of the chemicals. We could have put it in a baggie, okay, and passed it around. And when we did, it's the one that got really cold. So ammonium nitrate, ammonium chloride, they do the same sort of thing. Okay, so we got to break bonds between the ammonium and the nitrate. Okay, so we have that solid crystal. So first step is we have to take this stuff and break them some bonds. Okay, and then 2, the breaking the hydrogen bonds between the water molecules. Okay, so that's going to require some energy. And then we're going to form ion dipole attractions between the waters and the ammoniums and the nitrates. So that's going to be energy like this. And the temperature of the system decreases. So that tells us that from the beginning to the end, you know, for our potential energy diagram, it must be going uphill. So which of the following explains this change in temperature, explains the fact that we have a positive delta H? Okay, the sum of the energies required in steps 1 and 2 is greater than the energy released in 3. So if I said this and this is more than this, then I think that is exactly right. That looks like answer A. Okay, let's check the others. The sum of the energies required in steps 1 and 2 is less than. Okay, well, if it was less than, then it would go downhill more than it goes uphill, and that would be exothermic. All 3 steps release energy in the surroundings. No, one of them absorb, and release. And all 3 steps require energy to be absorbed. No. So 2 are absorbed, 1 is down. So the idea is from looking at this information, then we should be able to kind of visualize this sort of a diagram. Okay, this is endothermic, and then this one is exothermic. And we know that these must be greater than this because overall the temperature is decreasing, it's endothermic. Number 7. Okay, here's our bond diagram. Okay, we're talking about, here's 2 different CC bonds. And as they approach each other, okay, then the energy drops between them. Now what happens is that this becomes like a little spring, because as, you know, the 2 atoms get closer and closer and closer together, then they minimize their energy. But once they get very close together, so if I get like, you know, here's their equilibrium bond distance, but if I got them closer together, then they would start to repel. The energy would be higher. And it's sort of like if this were a little cup and I dropped a little, you know, sphere inside here, then it would roll back and forth and back and forth and back and forth. And it's the same thing that these spring, you know, if I give it a little pull, then it would bounce back and forth and back and forth. It would have a certain vibration. Okay, well, what we're saying here is, in the question, Which of these describes two interacting carbon atoms that are separated by 0.1 nanometers? So we're saying that this, so like on this graph, we're talking about something like right there. So if we're doing that, well, they're a little bit too close together, so they're going to push out. Their repulsions are going to cause them to push out. If they were out here somewhere, then the attractions would pull them in. Okay, if they were right here, they would, just kind of be in equilibrium and just sit there and vibrate. But right now, they're a little bit too close together over here, and so they're going to kind of repel. So what's that? The attractions between the atoms are stronger? No. The repulsions between the atoms are stronger than the attractions between the atoms, and the internuclear distance will increase. Okay, that's a fancy way of saying yes, they're going to push apart from each other. The attractions are maximized and repulsions are minimized, so it will not change. No. There are no attractive repulsive forces. No. Okay, the answer B for number 7. Okay, number 8. Given the following equations for the enthalpies of formations, okay, which of the following expressions represents the enthalpy of reaction for this following? Okay, so we have these three energies, three reactions, and we've got to build it into this reaction. So let's look for some key chemicals here. This first one here, here's P4O10, and I need P4O10, but I need it on the opposite side, and 1 and 1. So I have to take this guy, and I'm going to have to reverse it, okay, which means that my X is going to be negative X, not positive X. Okay, what else here? Here's H3P, no. So for these reactions, okay, over here, here's H3PO4, and I'm going to need it on the side it's shown, so that's okay, except I need 4 of them. So I have Z, but I'm going to have to end up doing 4 times Z in order to get my reaction. Now what about the middle one here? Okay, I've got H2O, and I'm going to need H2O on the left-hand side, so that means I'm going to have to reverse this guy. Okay, but I reverse it, I need 6 of these. Okay, and there's no other waters in these equations, so it's not like they're going to come from someplace else. So I'm going to need this equation, but I'm going to need it reversed, and I'm going to need it 6 times. So this last one had to be done 4 times. So instead of y, it's going to be negative y, and it's going to be negative 6y. Okay, so I am looking for some kind of an answer here that's got a negative x, negative 6y, and positive 4z. So 4z minus x minus 6y looks like answer A right here. And that's going to be my answer. Okay, so use the following data to find the standard enthalpy change for the following reaction. Okay, so again here we're just doing like products minus reactions, but we can do that with S's as well as other ones. What we have to notice here is that we will have a value for the element, okay, because these are not formation, they're not formation from its elements, it's just, the absolute entropy of things. So it's going to be the entropy of CuO minus the entropy of Cu, and subtract 1/2 the entropy of the O2. So my numbers are CuO 42, and these are all joules per mole Kelvin, or joules per Kelvin. Okay, minus, copper, which is 33, and minus 1/2 of the oxygen, which is 205. So 42 minus 33 minus 102.5, then I get negative 93.5, and that's joules per mole Kelvin. And that is answer B. Okay, number 10. Which of the following processes in the standard is the standard entropy of reaction expected to be negative? Okay, so negative delta S means that it is getting a little bit less disordered, less random. So we're looking for things that get less random. So A, solid going to gas. Okay, well that's definitely not getting less random. That's getting much more disordered. Aqueous, aqueous, solid, and aqueous. Okay, so we have 2 aqueous, 1, 2, 3 moles of aqueous going to solid and 2 aqueous. So that sounds like a possibility. Solid and liquid going to aqueous. Okay, that's definitely getting more disordered. And a solid going to gas, no way. Okay, so it must be answer B. Okay, so we have our aqueous things turning into a solid in aqueous. That's going to be a little bit less disordered. Number 11, ammonium chloride is placed in a container with water and the temperature dropped considerably. The reaction proceeds according to the following reaction. Okay, so ammonium chloride is going to dissolve. Well, I actually looked online and was able to find an actual little movie where they're taking some of this ammonium chloride and they dissolve it in water. And so one thing you can't really see here is down in the bottom they put a big drop of water and then put this on here. And what happens is that, when you stir the ammonium chloride, it gets so cold it actually, removes energy from the water, freezes it, and you can pick up the whole wooden block and this little teeny beaker at the same time. So that's kind of fun. Okay, so what do we know? We saw that the temperature drops considerably, and the reaction proceeds according to this equation. So what does that tell us? Well, if we know that it's getting colder, the surroundings are getting colder, okay, it must be absorbing heat. And if it's absorbing heat, then we know that the delta H is positive. So that's one thing. So we know delta H is positive, okay, which means delta H is greater than 0. So delta H greater than 0, so we can knock that one off, we can knock that one off. So we know it's not answer A or B. Okay, solid going to aqueous and aqueous, that is definitely getting more random. So our delta S is positive. So we're looking at these last two, delta H must be greater than 0, so we can knock off that one. So the answer has to be D. And the last little piece is, this actually does happen. You dissolve it in water, it does dissolve. So we know that the delta G must be negative, and so the delta G is less than 0, and that confirms our answer. Answer here is D. So just from the situation, we should know that delta H is positive, okay, because it absorbs energy. It is delta S is positive because it's getting more disordered, and since it does happen, we know delta G is negative. For number 12, for the reaction here, delta H is negative 114, delta S is negative 146. For which temperature is the reaction thermodynamically favorable? Assume the values do not change with temperature. Okay, so here's our equation. So what I would notice here is that our delta H is negative, and our delta S is also negative. So we already kind of know our situation here. If this is negative and negative, this is going to be spontaneous or thermodynamically favorable at low temperatures. And I have that just because I memorized that, but we can also see what's going on is that we have delta G equals delta H minus T delta S. We want a situation, if we want it thermodynamically favorable, we need delta G that's a negative value. Now this is negative, and that's going to cause my delta G to be negative. But the fact that this is negative, okay, that's not good, because negative will be a positive term. So if I have a small little temperature, okay, that'll make this term not so important, so it'll allow my delta G to be negative. So I knew this will be spontaneous at low temperatures. So what have I got? The process is thermodynamically favorable at all temperatures? No. The thermodynamically favorable above 778, we need no low temperatures. At only favorable at 778? No, we want it so it's below 778. Now, do we know that 778 is the key temperature where it changes? I'm going to have to assume that that's true. If we were to go back and say, well, at what point does this become, thermodynamically favorable? Then we're going to do the idea that, let's use the special case where this is 0. So 0 equals delta H minus T delta S. Solve for T. And I bet that's going to come out to be 778, because otherwise the question doesn't make sense. Okay, go on to 13. Given the following information, calculate delta G for this reaction. Well, we can see that we have delta H information, we have delta S information. Okay, we want to do delta G. Okay, we're going to remember delta G is equal to delta H minus T delta S. So we're going to calculate delta H, going to calculate delta S, and then we're going to go back and do this whole thing. Now notice it's 25 degrees. Let's change that to 298 Kelvin before we forget. And now we got some math to do. So what is the delta H for this reaction? Okay, it's going to be the delta H of So 2 times the delta H of H2O plus the delta H of O2, which is going to be 0 because these are formations, okay, minus 2 times the delta H of H2O2. Okay, so I have 2 times H2O, H2O, that's the negative 290, so negative 290 times 2 plus 0, okay, minus 2 times, for the H2O2 number, is negative 190. And so we can kind of see that I'm saying 2 times negative 290 minus 2 times 190. Okay, so I'm going to make that positive. And so it's going to end up being negative 200. Okay, now that's just my delta H. Okay, so that's my delta H value. Okay, I want to do my delta S value. So delta S, same kind of a deal. So it's going to be 2 times the, I'm going to change color, 2 times the H2O number, which is 70, plus my O2 number, which is 205, minus 2 times my H2O2 number, which is 110. Now I have to be really careful here because this one, okay, this was kilojoules per mole, and what I'm about to calculate now is going to be joules per mole Kelvin. So I'm going to have a 1,000 to 1 conversion I have to do in here somewhere, so I'll do that in a moment. So this part here, 2 times 70 plus 205 minus 220, then I get a value of 125 joules per mole Kelvin. Now I'm trying to get a value of delta G when I'm done, and so it's going to be in kilojoules. So I'm going to go ahead right now before I forget and change this into kilojoules. Okay, so I can see my answer here is going to be 0.125 kilojoules per mole Kelvin. Okay, so I've got two useful numbers here. Let's change colors. So my delta G is equal to delta H minus T delta S. So this is going to be negative 200 minus 298 times 0.125. Okay, and all those are going to be in kilojoules. Okay, per mole Kelvin. This is going to be mole in Kelvin times Kelvin, so kilojoules per mole. And for this I get negative 237, okay, 0.25. And that is in kilojoules. Okay, so there it is, answer C. Okay, and these other values, you can see what's going to happen. If you don't change your units, you're going to get some of these other funny answers. So watch out really carefully that this is in joules and this other one's in kilojoules. And you have to take that into account. And I did it right here when I changed my joules into kilojoules. So negative 237. Okay, number 14. Consider the following reaction. At 25 degrees, delta H is that and delta S is that. What is true about this reaction? Okay, so we're asking about Q's and K's, but the idea is if I know what my delta G is, then that's going to tell me about my Q's and K's. You know, that if I have a delta G that's negative, that is going to go forward. You know, it's a product favored reaction. So therefore my Q must be less than K. If my delta G is positive, that means it's going to go in reverse, which means my Q is greater than K. And if delta G is 0, then Q equals K. So it's not we can say nothing can be stated. We can do this if we know with a delta G value. So it's just time for us to go back and look at this. Now, this is positive and this is positive. Okay, so that means it's going to be temperature dependent. So I really need to go and calculate. So let's see here, this 225, I'm going to change that to 298 Kelvin before I forget. And we're going to use our same reaction, delta G, our same equation, delta equals delta H minus T delta S. And delta H is positive 133 kilojoules per mole. Okay, minus 298. And again, here, this is in joules, so I'm going to go ahead and change that to kilojoules. So I'm going to use 0.401. Okay, and then that'll give me kilojoules per mole. Per kilojoules per mole Kelvin times Kelvin, so kilojoules per mole. So let me calculate that. When I do this, I get a value of positive 13.353 kilojoules per mole. And I don't really care about the value, I really care about the sign. So the fact that my delta G is positive, then what that says is that this reaction is, the reverse reaction is going to be spontaneous. So I expect it to go in reverse. Now, if it's going to go in reverse, then that means that my Q must be larger than my K, okay, because that will cause it to go in reverse. So Q is larger than K. That is my answer. Okay, 15. The free energy change for a given reaction is negative 25 kilojoules. So somebody has calculated like we've done here, and they got that as negative 25 kilojoules. So what is the equilibrium constant for this reaction? Well, we can go back to our original equation that's on the AP exam, but remember we mushed that one around, and we learned that the K is equal to E to the negative, okay, delta G over RT. And so I want to get this value here and then take E to that value. So let's do that. So the first thing here, let's change colors. Okay, negative delta G, so I know it's negative, and my delta G is negative 25 kilojoules. That's a 5. Okay, and this time what I'm going to do is I'm going to change this to joules. So I know that I have 1,000 to 1. So 1 kilojoule is 1,000 joules. Now that's over R and T, so I know my R is 8.31. That's joules per mole Kelvin. Okay, 8.31. And my temperature is at 300 Kelvin. So my kelvins drop out. So this is joules per mole and joules per mole. This is a mole in here. Okay, so let's work out this answer. And when I do all this, I get a value of 10.02. Okay, but I get a value of 10. So that's coming back here. This is answer D. And this is saying that the value should be E to the 10. Okay, because we just figured out this little section, and that comes out to be 10. So E to the 10, which is going to be 2.3 times 10 to the 4. So the answer is D. Okay, so I'm running out of time, so I'm going to do the free response in a separate tutorial.